Now we come to a very important problem, one requiring a three-dimensional solution of the Schrödinger equation, which is the hydrogen atom. It's an important problem in its own right, and it's also an excellent model for all the atoms in the periodic table. So, a hydrogen atom consists of a proton of unit positive charge, an electron of unit negative charge, separated by some distance r. We should, it's a two-body problem, work in the center of mass frame of reference so that we have one distance treating one particle as fixed and the other as moving. However, because the proton has 2,000 times the mass of the electron, it's okay to consider this distance r as the distance between a fixed proton and a moving electron. Similarly, the reduced mass becomes essentially equal to just the mass of the electron, because the mass of the proton is about 2,000 times the mass of an electron. The interaction potential is the Coulomb potential. Epsilon 0 is the permittivity of free space. And so the energy of the final system given by the Schrödinger equation should depend just on this coordinate r. However, we need three quantum numbers. Remember, we had three quantum numbers for the free particle in three-dimensional space, because this is a three-dimensional problem, and we need to set the problem up in terms of three appropriate coordinates. Since the potential is just a function of r, it's sensible to use r for one of them, so we set the proton at the center of the coordinate system, and then choose polar coordinates for our two other degrees of freedom. However, we will see that while clearly one quantum number will be associated with r and determine the energies of the system, the other two quantum numbers cannot be associated simply with theta and phi. So, what are the right choice of quantum numbers? It turns out one of them is associated with one of the angles, usually phi, by convention, but the second one is associated with the quantity that is the total angular momentum of the system, that is the sum of the x, y, and z angular momenta squared, and we'll see why in a minute. Now, why can we not associate quantum numbers with each of these variables r, theta, phi? To see that, we have to understand what allows us to choose good quantum numbers in quantum mechanics. So let's go back to our free particle . Remember, for this particle, we had the result that the momentum was h bar k. So, for example, for the x momentum, h bar kx. This then lets us define a momentum operator as minus I h bar d by dx. This would be the x momentum operator, because if I take the derivative of e to the I kx, I get I k times phi. If I multiply this by minus I h bar, I get simply h bar k times phi. So with this momentum operator, I have a Schrödinger equation for momentum. P, or operating on the wave function, returns the wave function times the eigenvalue of the momentum. In three dimensions, this derivative d by dx plus d by dy plus d by dz, with the appropriate unit vectors in front of each of them, is written by this symbol. Now, we have seen that the eigenfunction of the Hamiltonian for a free particle, e to the I kx, is also an eigenfunction of the momentum operator. Another way of stating this is that if we operate on e to the ikx with the momentum operator, and then with the Hamiltonian, and then subtract from that quantity the Hamiltonian operating on the wave function e to the ikx, then operated on by the momentum operator, because the wave function is an eigenfunction of each of the operators, so the operation produces just the eigenvalue times the wave function, and the eigenvalue is not affected by the next operation. It doesn't matter how we carry out the order of the operations, so the result of this process of operating with the first operator and then the second operator and then the first, and subtracting the two quantities will produce identical results. We say that the operators commute, and we define a quantity called the commutator. So here is the commutator written out for the position operator, which is just x, and the momentum operator that we defined just a minute ago. If we try out the commutation operator on e to the ikx, so let's go ahead and operate on e to the ikx with x, and then operate on it with the momentum operator, and then take away from that the effect of operating with the momentum operator and then the position operator, we will discover that we do not get 0. We get the quantity I, h bar. It's said that p and x do not commute. This is a statement of the uncertainty principle. A more mathematical statement than the one we gave earlier, but stated now in terms of commuting operators. Operators that do not commute are therefore not eigenfunctions, do not have the same eigenfunctions. If we go now to the angular momentum operator to return to the problem of the hydrogen atom, in classical mechanics, the angular momentum is given by the cross product of position and linear momentum, and you see here the expression for the operator for the x component of angular momentum in quantum mechanics. It looks a lot like this classical expression, with similar terms for Ly and Lz. And so if we try out commutation operations with Lx, Ly, and Lz, what we discover is they do not commute. So the angular momentum states cannot simultaneously be eigenfunctions of the Hamiltonian. So Lx, Ly, Lz are not simultaneously eigenstates. This means we have to pick on one of the rotations, say the phi rotation, Lz, as our eigenstate. And this then leaves us one eigenstate associated with R, another eigenstate associated with phi, for which we will use the quantum number m. And we need a third eigenstate because we are in 3 dimensions. It turns out that the appropriate eigenstate is an eigenfunction of the angular momentum squared operator, written down here in polar coordinates. And these 3 variables then, the distance between the proton and the electron, a rotation around one of the angles chosen arbitrarily to be phi, and the eigenvalue, the so-called azimuthal quantum number, corresponding to the eigenfunction of the angular momentum squared operator, give us our 3 quantum numbers for the hydrogen atom.